So next speaker is Dominik Wehrle, talking about stubborn sets for fully observable non-deterministic planning.
Hello, I'm Dominik Wehrle, and this is a joint work with Yusra Alkhazraji, Michael Katz, and Marty Wehrle about stubborn sets in fully observable non-deterministic planning. First of all, fully observable non-deterministic planning generalized the classical planning formalism in the sense that we can have non-deterministic operators. So these are operators which can lead to multiple successor states. They have multiple effects. And also the plan notion we are after in font planning is different from what we have in classical planning. The plan notion we have here is a strong cyclic plan. That's some tree structure like thing like this here. If we apply the actions top down, we will eventually get to a goal state. That's the property of it. And the approach we follow is an font planning as a Leo star search. So we use the algorithm which has originally been proposed for MDPs by Hansen and Silberstein and adapted to the font setting by Matt-Müller et al. And this approach is basically it's working on the font planning as its font problem as itself. It is an AND/OR graph search. In contrast to what A star is it's an OR graph search, and because if we apply an action, we might also care about multiple successor states in contrast to just one, as in classical planning. And this is a heuristic forward search, similar to A star. A little bit on the motivation of partial auto-reduction. Partial auto-reduction is an idea to exploit the independence of operators. What does that mean? If you look at this diamond, we see this is the initial state of a transition system. This is the goal state. In order to get from here to there, we have to apply these three operators, but it's actually not of importance in which order we apply them. And that's exactly where partial auto-reduction comes into play. Partial auto-reduction wants to get rid of this unnecessary blow-up that we would have if we would apply all the orderings. And strong stubborn sets are the most prominent approach in optimal planning for partial auto-reduction, and they have been introduced by Wehrle and Telmert in 2012. Well, sorry. That's the roadmap of my talk. I will first present a slight generalization of strong stubborn sets, the so-called weak stubborn sets. Then I will try to apply these weak stubborn sets to font planning in determinizing the font planning problem. See that this is actually not possible as easy as we think, and introduce attachability, which is a new criterion on completeness preserving state space pruning techniques. And I will then take this attachability criterion, implement it in the non-deterministic weak stubborn set, and the resulting stubborn set will be completeness preserving for font planning as well. All right. Before defining weak stubborn sets, I will give you a few definitions. First, we have a slight generalization of what a disjunctive action landmark is. A disjunctive action landmark in our case is basically we have a partial state S prime. We are in a state S, and a disjunctive action landmark for the state S for the partial state S prime in that state S is basically a set such that if any path from S to some state that is subsumed by its prime contains at least one operator out of the disjunctive action landmark set. And a special case of this is the so-called necessary enabling set. This is a set which does the same for the precondition of an operator, and that we will need in order to not to rule out the possibilities that arise if we have if we have inapplicable operators in the search. So this is kind of a necessary condition not to rule out the currently inapplicable the possibilities by the currently inapplicable operators. All right, this is the second definition I want to give you. And this is absolutely crucial to this stubborn sets idea, because this is basically what it's all about. The idea is of partial order reduction is that order should if order doesn't matter, we should detect that. And to do that, we actually want to see when order matters. And this is exactly what we see here. We call two operators interfering with each other if we either have this picture, which means we are in a state, have two applicable operators, and one of those disables the other one. That's this picture. Or we have this situation here where the two operators just lead to different successor states. And therefore, the order actually matters in which we apply them. All right, now comes the weak stubborn set definition. As said, this is a slight generalization of the definition by Wehrle and Helmert in 2012. And basically, this stubborn set is computed state-wise. So we compute that in any state. It's a subset of all operators, and a search algorithm would just apply all the applicable operators out of that set. But we have three conditions that we need to consider. We include a disjunctive action landmark. That's kind of the intuition behind that is to still have a goal-directed search. And the second condition takes care of the inapplicable operators and adds a necessary enabling set for them in order not to lose track of all the possibilities that arise by the currently inapplicable operators. And the third condition, basically, well, this is actually only that if two operators are applicable, we have exactly this situation, and if that happens, we actually have to care for that and have to add the operator to the stubborn set as well in order to consider the order. Oh, that's a good joke. All right, now a small example on that. We have two operators. We want to construct such a stubborn set, and we can do that by first adding a disjunctive action landmark, which is O1 in this case, because it achieves some fact which is relevant to the goal. And after that, we look, there are no inapplicable operators, so the second condition does not hold here, so we don't have to consider that. And for the third, we look whether there are operators that weakly interfere with each other, and that's also not the case. So the singleton set here is a weak stubborn set in 0, 0. A search algorithm like A star would only apply O1 with partial order reduction turned on. All right. So far, this was only in the deterministic world. So this was about what's done in optimal planning, slightly generalized. But now comes the question: how can we actually adapt that to non-deterministic setting? How can we do that in font planning? And the first idea would be we could determinize the font planning problem. Then we only have deterministic operators. And then just apply the weak stubborn set formalism we have seen on the last slide. But that idea turns out to be incomplete. So that will not preserve our plans. And here I show you why. So imagine you have this strong cyclic plan given. Like you have 4 operators which directly lead to the goal from those 4 states, and they don't lead to the goal from anywhere else. They are just applicable in exactly these 4 states and nowhere else. And furthermore, you have 2 operators which work on distinct variables. They don't. The first one just sets the first variable to 1 or 2, like this is a 1, and the second one does it for the second variable. And that kind of, we might think now we might change the order of these two operators because they seem to be independent. Yeah, let's do that. So the middle picture shows this situation. We start with O2 instead of O1. We get these two successor states. But if we now apply O1, then we will get such a state where this first variable is set to 2 and the second is set to 1. And from there we don't have an operator which leads to the goal. So this is definitely not the idea we should follow for font planning. And we came up with a new idea towards that, and that's called attachability. So what stubborn sets what we have seen is that stubborn sets permute operators, right? And instead of doing that, we attach operators. So if you look at this figure, you see if we have a plan that starts with O2 and leads to the goal, and if we can safely attach a 1 to its front, then we call the resulting like a 1 attachable to O2. And yeah, that's the criterion we have for deterministic operators. Now we bring this in the non-deterministic world. We basically, if we can do this transformation here, if we have a strong cyclic plan there and can have an operator 1 which is attachable to any outcome of O2, we will get this situation. And that's basically what stubborn sets in font are about. Now we will integrate this idea into weak stubborn sets. The condition 1, 2, and 4 are identical to what we have in weak stubborn sets for classical planning, but the only difference is this third rule here. And this third rule only says that for all applicable operators, we need to check this situation here. If this is possible, we don't have to add the operator. If it's not, we have to add the operator into the set in order to not lose track of some possibility that can arise. All right, and we have in this work we have shown that such a non-deterministic weak stubborn set is completeness preserving for font planning. And this can also make a strong stubborn set if we require the interference relation and the accordance criterion to be symmetric. But that would that we have also only considered because there is a slight difference in approximating these relations. So now I come to my empirical evaluation of the stubborn sets. We have considered the two variants, the weak stubborn set and the strong ones. And the setting was an ALEO star search using FF heuristic on the all outcomes determinization. And yeah, the usual bounds and memory limits. And our proof in concept implementation shows at least some small noticeable improvement in performance, which shows us that this theoretical concept is applicable also in practice. And future work might be on making this even more efficient. And here we also have the node generations. There we, like on the x-axis, we have a regular ALEO star search with FF heuristic. On the y-axis, we have on top of that we have non-deterministic weak stubborn sets. And everything below the line basically shows where our method works really well. In some cases, it's really exponential, the reduction. In a lot of cases, it just reduces the state space a bit. But there are also some cases where the stubborn set misguide the search, so these are the dots above the line. And the effects are a lot less pronounced if you use the strong version of it. So there's an actual difference between using weak and strong stubborn sets in font planning. And in a second experiment, we have combined non-deterministic weak stubborn set with active operator pruning and symmetry reduction. Symmetry reduction we just presented at ICAPS 2016, also for font. They were straightforward adaptation of what we have in optimal planning. And yeah, long story short, we have seen that the overall combination of all three methods is really beneficial to the search. Right. To wrap up, I've introduced weak stubborn sets to classical planning. These are is a slight generalization of strong stubborn sets. We have generalized the theory of stubborn sets for font planning. We have seen that this is actually non-trivial to do. We have introduced a new idea of state space pruning based on attachability instead of commuting operators, which can also be used for in classical planning, for instance, for ansatz problems. And we have implemented this into the non-deterministic weak stubborn set and evaluated a first prototype implementation and saw strong synergy effects with symmetry reduction and active operator pruning. That's it. That's what was my talk. Thanks for yeah. That's it.
Questions? So, all the results that you presented about the non-deterministic case, right?
Yes.
Have you some preliminary experiments on weak stubborn sets for the deterministic case, or?
Yeah, we have run some experiments, but they actually don't. What's interesting is that they don't make a big difference, at least on the IPC domains from classical planning, but they do on the font planning instances, at least to some degree.
Yeah. Maybe I missed it, but what is the meaning of a landmark in a non-deterministic problem?
Well, we have used the notion of landmarks for the determinization. Basically, it's basically meaning the same as in the classical setting. So
it's landmarks of the all-up indeterminization?
Yes.
Okay.
Yes. Yeah. I think Christian wanted also.
Yeah, you can ask the question.
Yeah, the results went by pretty quick. Can you say which domains in particular did it work well and did it not work well? And do you have any insight as to why in some domains it works and others it doesn't?
It works particularly well in forest because there we have a lot of independent operators. It does also work good in first responders, but not as good as in forest. But yeah, I mean, independent operators are the main cause of that. I've also checked the other domains. They don't seem to have many of independent operators, so they often don't have. They don't even have diamonds in the state space, so they don't. Right. Does that answer your question?
Yeah. Thanks.
All right. That's question. So let's thank Victor again.